In the last section, we introduced some aspects of the attacker's perspective, showing how they can exploit various vulnerabilities in authentication. We examined how attackers can guess or capture credentials in password-based systems and intercept OTPs through vulnerable communication channels. We showed why MFA has added layers of difficulty to the attack process. Now, attackers are increasingly shifting focus from technology to people, employing methods that exploit human behavior rather than purely technical weaknesses. In this section, we'll dive into the techniques of MFA bypass with a close look at the MFA fatigue attack. Following that, we'll analyze an adversary-in-the-middle setup and how attackers leverage it to bypass MFA defenses. Let's get started. Typically, MFA is based on your password combined with another factor, like a prompt on your phone or a code. To trigger that second factor, the system usually requires the correct credentials first. So, for an attacker to even attempt an MFA bypass, they usually need to know your password. But how could they get your credentials in the first place? Actually, there are quite a few ways this can happen. One common way is through a database leak. For example, you might have signed up for an application that later got breached. If you use the same password for that app as you do elsewhere, anyone who has that database now has your password. And these leaked databases aren't hard to find. They're often available on dark web forums. Another way attackers capture credentials is through recording methods. They could use direct observation, hidden cameras, or software called keyloggers that record everything you type. And then there's the risk from password managers and browser storage. If these aren't properly secured, they can also leak your credentials. Of course, these aren't the only methods given the creativity of attackers. But the key point here is that attackers generally need to have your credentials first before they can attempt a straightforward MFA bypass. MFA bypass through social engineering is a common tactic. Imagine this scenario. You've had problems with your authentication app before. It's been unreliable at times, and there was even one occasion where you had to call support to get it sorted out. Now things are working fine, but suddenly you see an unfamiliar authentication attempt pop up on your app. You don't recognize it, so you decide to ignore it. But then your phone rings. It's someone claiming to be a support engineer. They tell you there's an issue with the authentication system and that they need to verify your access. They ask you to approve the prompt that just showed up. Seems believable, right? It doesn't feel much different from an actual support call. But in reality, this is a classic social engineering attack designed to bypass your MFA. Here's what's actually happening. The attacker already has your password and just needs you to approve the MFA prompt to gain access. By framing it as a routine support call, they trick you into authorizing them. The more believable the story, the higher the success rate for the attacker. So the setup for an attack often begins well in advance. For instance, the user might receive a fake notification about upcoming maintenance on the MFA server to lower their suspicion and make them more likely to trust an unusual prompt later on. This example shows how attackers use social engineering tactics to work around security systems that rely on MFA. What is fascinating is that MFA was not broken, the user just let the attacker in. The previous example actually requires some effort from the attacker. It is not that simple to pick a vulnerable user, build a story, and execute it with confidence. So is there anything easier to bypass MFA? Do you remember the brute forcing approach to cracking passwords? What if we apply the same logic to MFA? An attack known as MFA fatigue or MFA bombing follows a similar approach. Here the attacker bombards the victim with repeated MFA prompts, hoping that frustration or fatigue will cause the user to accept at least one. And one is all it takes to compromise the system. Luckily, we have ways to protect ourselves. One effective approach is to link the action that starts authentication with the confirmation process itself. This ties any out-of-band channel, like push notifications, directly to the user's session. Here's an example. The user initiates a push-based authentication. The server responds by doing two things. It sends a push notification to the user's device and displays a verification code in the web browser. The user receives the push, is asked to enter the code, copies it from the browser into the app, and the app sends it back to the server for verification. The result? It prevents users from accidentally approving unknown MFA requests. Let's look at a similar example, but this time from the attacker's perspective. In this scenario, the attacker triggers MFA and gets the code. Our user gets the prompt, but it is unlikely for her to guess the correct value. Simply speaking, if you didn't trigger the prompt, you're unlikely to know the number, making it harder for an attacker to force acceptance. This mitigates simpler attacks, but in the case of social engineering, attackers can still manipulate users into entering the correct code. Although it may already seem easy enough to bypass, attackers have yet another method to get around MFA. Let's explore it in the next section. Now let's explore one more attack vector, which is especially tricky because it uses a legitimate feature and operates passively, without direct engagement from the attacker. This attack is known as Adversary-in-the-Middle, and soon you'll see why. You may have heard the phrase, "It's not a bug, it's a feature." Well, in this case, the feature being exploited is the way network traffic travels through multiple devices and servers. When you connect to a website, your request, along with your credentials, first goes to your home router, then to your network provider, and through several other hops before reaching the destination server. At each of these hops, the content of your request can potentially be read. To prevent this, we use transport layer security, which secures data as it travels over the network. When you see HTTPS in front of a website URL, it means TLS is active. TLS creates a secure pipe between 2 points, your browser and the server, ensuring that no one can intercept the data in transit. This is great because TLS prevents anyone from snooping on your sensitive data. But there's a downside, especially from a corporate security standpoint. TLS encryption means that even organizations can't inspect outbound traffic to detect potential leaks of confidential data, like someone sending sensitive company information to competitors. So how do organizations solve this? They can introduce a proxy at the network edge. This proxy intercepts and forwards all traffic passing through it, enabling inspection. However, since TLS encrypts traffic, the proxy alone isn't enough. The solution is TLS terminating proxy. This proxy breaks the TLS connection, decrypts the data for inspection, and then re-establishes a new TLS connection on the other side. This allows traffic to be analyzed in plain text, letting organizations detect malicious activity. This setup is sometimes called man-in-the-middle, because the proxy acts as an intermediary that can read the traffic between the user and the server. Now, you might be wondering, wouldn't your browser detect this? By default, yes. Your browser doesn't automatically trust every website. It only trusts sites verified by specific companies known as certificate authorities, which specialize in issuing trusted security certificates. In a man-in-the-middle situation, if someone tries to intercept your connection, your browser will alert you, unless you manually override the warning. In certain environments, like a company network, each device can be set up to trust the organization's proxy, so the browser won't raise any alarms. So what happens when the man-in-the-middle becomes an adversary? That's when we get an adversary-in-the-middle attack. Imagine that instead of an organization's proxy, attackers set up a malicious proxy, perhaps using a cloud provider, and trick users into connecting through it. Why would anyone use a proxy like this on purpose? And wouldn't the browser notice? Usually people wouldn't willingly use a malicious proxy, but that's where phishing comes into play. Attackers set up a malicious proxy with a domain that looks almost identical to a legitimate one and get a certificate for it. It's simple to do, and it's a legitimate process of creating a web server. Since the site uses HTTPS with certificate from Trusted CA, your browser won't flag it as suspicious when you visit. From there, the attacker just needs to trick you into clicking their phishing link, often through a realistic-looking email or message. So let's see what happens when you fall for it. Your browser opens a TLS connection to the attacker's proxy. The proxy opens a second TLS connection to the legitimate server. The server sends back the web page, and the proxy forwards it to your browser. The critical thing to note here is that the website looks identical to the real one. It's served directly from the legitimate server, so the only giveaway might be the slightly altered domain name, but that's easy to miss. Let's see how authentication is broken if the user falls for the phishing bait. Now, when you attempt to log in, your credentials pass through the attacker's proxy, allowing them to capture your username and password in plain text. If password authentication is your only defense, it's game over. But wait, don't all those 2FA methods we've discussed before protect against this? Shouldn't a one-time password or push notification stop this? Unfortunately, no. While it's true that attackers can't reuse a one-time password or push notification, they don't need to. Instead, they capture what comes after, your session cookie or session token. These tokens represent an active session with the server and are typically treated as bearer tokens, meaning whoever holds the token has access. Once the session token is captured, the attacker can impersonate you without needing your password or MFA. In this type of attack, the user remains completely unaware that their password or session has been stolen. From their perspective, everything appears as usual. Let's take a look at a real-life demo of this attack. In this scenario, our attacker is trying to gain access to a GitHub portal. GitHub is widely used for storing and managing software source code, so the attacker's goal might be to steal the code for a secret project. This stolen code could then be sold to competitors or analyzed for vulnerabilities that could be exploited on the production server. It's important to note that this isn't a weakness of GitHub itself, but of the authentication method being used. GitHub provides strong authentication options, which we'll discuss later. For this attack, the attacker has set up a man-in-the-middle proxy using Evil Jinx, an open-source tool designed to demonstrate this type of attack. The attacker also configures a phishing domain, in this case githubcybersoup.org, and crafts a phishing email containing a deceptive link. The email is sent to the victim, and now the attacker waits for the victim to take the bait. Now let's see the attack in action. First, we'll look at how the victim logs in. The user opens github.com. Then the user provides their username and password. The account is protected by TOTP, so the user also enters a 6-digit code. After this, the user successfully logs into their account and can access the secret project code. Now let's see how an attacker can prepare and execute an attack against this account. In this demonstration, actions performed by the attacker are marked with a red attacker sign, while the victim's steps are marked with a green victim sign. The black window you see is a terminal connected to the attacker's server, where the attacker runs commands to configure a man-in-the-middle server. The attacker starts the Evil Jinx server. This tool provides a list of available configurations, each designed for different services. You might notice familiar names like Okta, Reddit, Microsoft, and LinkedIn. For this demo, the attacker only enables the configuration for GitHub to capture its credentials. Next, the server generates a unique URL. This URL is designed to direct the victim to the attacker's server rather than the real GitHub server. Now let's check the victim's email inbox. As you can see, the attacker has sent a phishing email that closely resembles a genuine message from GitHub. The email includes a green button, but if you hover over it, you can see it redirects to the malicious URL instead of GitHub's legitimate site. Let's see what happens when the victim clicks the button. The victim's browser opens what appears to be the GitHub login page. However, the URL is not GitHub's real domain, it belongs to the attacker. As soon as the victim opens the URL, the attacker is notified on their server that a new visitor has accessed the link. The victim proceeds to enter their username and password. The attacker immediately captures these credentials. If the account relied solely on these credentials for security, it would already be compromised. However, this account is also protected by OTP code. While still on the malicious side, the victim enters the OTP code. The login process is successful and the victim is logged in. Now let's see what the attacker has captured on their server. The attacker's server logs all the tokens generated during the victim's login process. These tokens are displayed in a table and attacker can view the details. The server captures all the cookies associated with the session and displays them in JSON format. This format is particularly useful for attackers because it can be injected directly into a browser, and that's exactly what our attacker will do. In the attacker's browser, you can see that no account is currently logged into GitHub. But by injecting the stolen JSON cookies using a Chrome extension, the attacker can bypass the login process. Injecting the cookies configures the browser to the same state as the authenticated user. After reloading the page, the attacker gains full access to the victim's account, including the secret project, which can now be stolen. So where does that leave us? Does this mean almost any authentication method could fail in this kind of attack? Not quite. The key to stopping adversary-in-the-middle attacks is to use authentication methods that verify the integrity of the communication channel itself. Passwordless methods, especially those based on cryptography, provide this kind of protection, and we'll dive into them in the next section. But before we move on, let's recap what we've covered so far. We started by looking at a non-technical social engineering approach to bypassing MFA. Then we talked about how attackers can overwhelm users with repeated MFA prompts, hoping one will eventually be accepted. After that, we discussed how vendors are trying to counter this by introducing user-specific mechanisms like copying codes. Finally, we explored how adversaries can use man-in-the-middle setups to steal credentials and session tokens. Now I think we're ready to dive into passwordless authentication.